All right, so today I'm going to talk about the four sources of packet delay, and then I will work on a problem that shows you how to incorporate all these types of delays and to determine the final no delay. So first of all, I took this from one of the lectures in Module 1, and I thought it already summarized these four types of delays pretty well, so I'll just go over them pretty briefly. So first of all, we have nodal processing delay, which is essentially just a packet. A packet gets checked for any bit errors, and it's the delay that for basically how long it takes to process a packet through some type of device, like in this case, maybe a router. And then here we have queuing delay, which is essentially just the amount of time that you'll have to wait to process through that said tool. So let's say we have like 10 packets here, and well, the 10th packet is going to have to wait for 9 more packets in front of it to process through the tool. Simple as that. Then here we have transmission delay, which is basically just the amount of time it takes to process through that said tool. And then propagation delay is simply just the amount of time it takes to process that packet through a specific like physical landline. Let's say like, I don't know, some fiber link wires or something like that. Anyway, hopefully that's a somewhat decent summary of the couple different types of delay. Okay, I'll go through the problem now. So, okay, so I took a problem from our, I think, module 1 and decided to modify some of the numbers a bit to uh, go over a simple problem that portrays some or most of the delays properly. So here we have a voice over IP problem. And basically we have this packet that will be converting from analog to digital. Um, and it'll go through some type of device here, which will incur a transmission delay. And then it goes through some type of physical link here to get to our host B, which is, sorry, this link here will be our physical delay. It's portraying our physical delay. So here we get all the values that are involved. They've this problem already nicely placed everything into certain variables for us. So L would be, just for L over R and everything. The total amount of distance traveled, speed. So basically, this problem was asking how much time does it take for um, from t of 0 initial time for the first packet to get sent to host A to host B and back. Um, so I'll go through the simple concepts that are involved here. So first of all, we'll just go through the simple overall equation to solve for nodal delay, which is basically just the 4 different types of delays involved. So process delay, queuing delay, transmission delay, and propagation delay. And as you can see in the first example, or not the first example, but the question, it's only asking about one packet. So we can make the assumption that there are 0 packets waiting in front of this one packet. So you can just set DQ to be 0 and just get rid of that entirely. And then you can keep on going further on and just make it a little simpler and just get rid of the queuing delay. Then you can simplify it into these 3 different variables, basically. So you can say that the processing delay is the time that it takes for the packet to be converted from analog to digital, which in this case would be L, which is the size of the packet. and A is the conversion rate. And then similarly, you have transmission, which is just your L over R, your packet divided by your transmission rate. And then your propagation rate, which is just the amount of distance the packet has to travel over the time it travels through. So first of all, the simplest thing you can always do is just convert the packet from bytes to bits, since all of our rates are always in some manner of megabits or kilobits. So it just makes more sense to just go ahead and convert that immediately. And then I'll just go through like the simple calculation process for each of these steps. So first of all, you can go through process and just do L over A, which is 3 or 4 bits divided by 30 kilobits, the analog conversion rate. And then you have to convert this to bits per second. And via that conversion sheet given to us in module 1, you can determine that there's 10 to the third power, or 1,000 bits per second over 1 kilobit per second. And then you can get this answer of 0.0128 seconds. And then here we do the same thing basically, but rather than kilobits, we now have megabit, which is 10 to the 6th bits per second. And you convert once again, and you get this answer, 7.53 times 10 to the negative 5 seconds. And I mean, rather than converting all of these to milliseconds now, which would make sense, I prefer to just keep it all unsimplified, and I'll leave the conversion for the very end. And then here I can calculate the values for propagation delay, which is essentially just the distance divided by the conversion, the travel rate. So this is 1,240 kilometers, and we know that there's 1,000 meters per kilometer. So multiply by 1,000, and you divide by the time, or the speed here, which once again, we get a value 0.00496 seconds. And then to get your final answer, all you have to do is just add all these values up together, and you'll get this in seconds, which is not really ideal, since I guess majority of the time we try to get rid of any leading zeros. So I multiplied by 1,000 to get this answer in milliseconds, since there's 1,000 milliseconds in a second. And then you get 17.84 milliseconds.